111. Water flows over Niagara Falls at an average rate of 4 million CFM and drops 170 feet to the base of the falls. The rate of change of gravitational potential energy in megawatts is most nearly what? So in terms of a formula, I remember potential energy equals mgh, but I wanted to find a formula that you could actually refer to. So I got equation 22.9, version A for imperial units, and it says work equals mg h2 minus h1, which is sort of like change in height, right? Which we have here. This thing's dropping 170 feet. But the problem with this is it's going to come out in energy units. And what we really want to know is the rate of change of gravitational potential energy. So we want an energy per unit time. And it's interesting because we have a volume flow rate, not a volume. So if we were to just adapt this formula slightly by making these rates, so instead of this being energy, let's have it be an energy rate. And instead of this being mass, let's have it be a mass flow rate. Now, instead of potential energy, or just energy, we're getting energy per unit time and mass per unit time. So this formula will actually work out pretty well for us. And instead of h2 minus h1, we already know it drops 170. So we can just say that this is 170 feet. So with that, let's take a shot at substituting everything in there. So the rate of change of energy, and I'm using W dot. You could use PE for potential energy, but the point is the dot to show that it's a energy per unit time. But energy is work, so I'll just use W dot. And we want first M dot, but we don't have M dot, we have volume flow rate. So let's start with the volume flow rate then. It's 4 times 10 to the 6 CFM, so cubic feet per minute. Ultimately, we're trying to get to megawatts, so we really need to get to SI units. So let's convert the cubic feet per minute into liters per second. So the conversion there is 0.472 liters per second per CFM. If you ever need to do a problem where you just make a rough approximation, you can remember that there's 2 CFM for every liter per second, or half a liter per second per CFM. And then the convenient thing about SI units, there's many convenient things about SI units, but one of them is that a liter of water weighs 1 kilogram. So now we have a mass flow rate because we got rid of CFM and we got rid of liters, so we now have kilograms per second. And now we want to multiply by gravity, which is 9.81 meters per second squared. And now we need that height, so that's 170 feet, and we need that in SI units, so meters would be better. So times 1 meter, a meter is 3.281 feet. If you're in a pinch, you can just use 3.3. You always want to have unit conversions that you kind of memorize, even if they're not exact. And then if you have time to get the exact number, that's of course better. But some of these answer choices aren't that close to each other, so you may be able to get away with some quick rounding. All right, so now we got rid of feet. And let's see where we are in terms of units. If we take these two together, we have kilogram meter per second squared. Well, that's a Newton. And now if we throw in meters and divide by seconds, we have Newton meters per second. Well, a Newton meter is a joule, so it's joules per second. And joules per second is watts. And ultimately what we want is megawatts. So we are going in a good direction here. So W dot is 956,651,813 watts, or 957 megawatts. And that's pretty close to answer choice C.